Hi viewers, welcome back to the course. Today we are here with another problem from the textbook Mechanics of Materials written by Timoshenko and Gere. This problem has something to do with the thermal effects that usually considered for structures which will see a variation in temperature. A good example will be a spacecraft structure which when put into space will see temperature excursions from minus 50 degrees Celsius or minus 100 degrees Celsius to plus 100 plus 150 degrees Celsius. So how structures are going to behave under this kind of temperature excursions, that will be of keen interest to people who are working in those fields. So today we will look at an example. Coming to the problem here we have a bar which is rigidly fixed at these 2 points A and B. To much of our interest, there are no external loads acting on the structure, but what we are going to do here is increase the temperature. That too, increase the temperature uniformly by an amount of 50 degrees Celsius. And see what are the stresses, what are the axial stresses that gets generated in these bars. Make sense? And we will also compute what is the displacement of this particular point C. See, first of all, this is a statically indeterminate problem because we have two reactions at points A and points B. Now, if we enforce the force equilibrium, since this being a uniaxial problem or a one-dimensional problem, we have only one equation, that is sigma fx equal to 0. But we can't solve for the two unknowns, which is a reaction at A and reaction at B. So what we are going to do is, it's a very standard technique. The technique goes like this. For the time being, I will remove one support. When I am removing one support, I will additionally add a reaction force at this particular point B. Then the problem becomes statically determinate. Then I will solve the problem like a very normal problem with no magic involved or with no more assumptions involved. So I will treat this reaction as an external force and compute the deflections. Once the deflections are computed through this method or through this technique, then finally I will bring back to this problem. I will enforce the condition that comes from this problem. What is that condition that comes out from this problem? For this problem, the displacement at B should be 0. So then we will solve for what is reaction at RB, and then we will compute the deflection at the point C. When you get a problem where so in effect we will be solving this problem, we will be solving this problem like this. So I removed the support from here, then I replaced that with a force capital R1, with an external force R1, or it is actually reaction force, but for this problem this R1 can be treated as an external force. Then see, there are two things which can cause deformations in this particular assembly, in this particular system of bars. Those two things are, first is the thermal. So the thermal effects will cause elongation. Then this particular external force can also cause elongation. For the time being, first let's focus on the deformations caused by the thermal effects, which are fairly easier to compute. So how we will compute that? So the formula is given here. It's a very simple formula. The thermal strain is given by alpha delta T, and in this case I am interested in the deflections of each of these segments purely due to thermal effects. So this is the delta 1, the amount by which this particular segment extends, and delta 2 is the amount by which this particular segment, the thicker space portion, extends. All the values are given in the problem, so it is just plug and chug. Once you plug those values, you will get I've done it here. So you will get delta 1 is equal to 1.5 mm and delta 2 equal to 3 mm. Once again, please remember that These deflections are coming because of purely thermal effects. Now we need to account for the deformations caused by this force, this external force, capital R. That's what I have shown over here. So this particular segment will get further extended by an amount delta 1 superscript R. This is caused by this particular force, capital R, and this was coming from thermal effects. Similarly, the second segment also will be further elongated by an amount delta 2 superscript R, which is again due to the force capital R, which is shown over here. Make sense? So a simple formula, because you know this particular force capital R will be acting throughout this two sections. So the external force acting on this section will be capital R, and this section will be again capital R. Now when I compute delta 2 because of the reaction force R, it is given by this formula. Now I am plugging in values. See, when you are plugging in values, always use consistent units. I like to work with Newton per millimeter square, that is megapascal, and millimeter. This is it's a set of units that I use it for simulation when I'm doing simulations on ANSYS, and I just love working with this unit. So it depends upon person. You can use whatever units you love working with. Now the point is, now you get delta 2 R. When you have used consistent units, this displacement will be in mm. If you have put your Young's modulus in MPa, and when you have put your A2 in mm square, and when you have put your R in newtons, and when you have put your L2 in millimeter, then you will end up with delta 2R having units of millimeter. Similarly, you can compute delta 1R, which tells you how much the first segment of the assembly extended only because of the external force capital R. Then you will get an expression like this, on divided by 24 into 10 cube millimeter. So now you have computed for this problem, not for the original problem. Now you have computed what is the total deflection for this problem. So if I ask you what is the deflection at this point, then you can simply add all these together. Why? Because see, the displacement at this point, it's a summation of all the points. It's a summation of displacements of all these points. Make sense? Now you are solving a different problem where this particular portion is fixed. So in order to impose that constraint, once you add all these things together, you should get a value of 0. That can be thought of as a compatibility constraint, because in the real problem the displacement at the right extreme point is 0. So that can be thought of as a compatibility problem or a compatibility constraint. Once you enforce that constraint, then this is the formula. Now you have values for everything, all these quantities. Once you put in the numbers, then you can solve for what is the reaction force R. This is the reaction force. Why there is a negative sign? Let me explain you that in a while. See, initially you thought that R is acting towards the right, but you got a negative value for R. That means in actual scenario, the R is acting in this direction. So this is the direction in which capital R is acting. Makes sense? Because the bar is trying to elongate, and from the right wall there is a compressive force that says, hey bar, don't elongate, you are not allowed to elongate, you have to stay at the same position. It can be thought of as something like that. Makes sense? Now you computed what is the reaction force. Then if you want to compute the maximum stress, it is fairly easy, because see, this particular R, where I can show this is the direction in which R is acting. This R is acting at this section, and it is acting at this section as well. So the maximum stress will occur at this section. It will occur at this section, and its value can be computed like this. where 1200 millimeters square is the cross-sectional area of that particular section. So the maximum stress will come around 38.6 MPa. Again, use consistent units. Another interesting problem. See, they're asking you, this point didn't move. This point didn't move. It stayed at that point itself. But what about points, this point? Believe me, this point has moved. This point has moved. This point has moved by an amount delta 1, which is coming from the thermal effects, and delta 1 r, which is coming from the from this external force effect. Once you add these two things together, then you will get displacement at C. So the displacement at C is fairly straightforward, because you have non-expressions, or you have evaluated the expressions corresponding to delta 1 and delta 1 r. So it is just plug and chug once again. Once you do the plug and chug, then you get a value of minus 0.43 mm. What does that mean? See, minus 4, let me explain that here. So for this particular problem, since we assume this is the positive direction of the force, if you get a positive displacement value, that means the displacement is along this direction, that along the direction same as that of capital R. But it is coming to be negative. That means actually this particular point, let's call this particular point C, it in fact moved to the left, not to the right. So C has moved to the left, not to the right. So you can say due to thermal effects, it has elongated by some amount, but then because of this capital R, which was acting in this direction, or which is acting in this direction, this point has further moved to the left. Makes sense? So R is more superior. The displacement due to R is more superior than the thermal effects. So that's why that point has gone to the left. Just one more thing before I wind up. Had this bar was of uniform cross section, let's say something like this, and even if we increase the temperature, if we increase the temperature by the same amount, let's say delta T equal to 50 degrees Celsius, in this case it is of constant cross section, then the total strain at this point is 0. Makes sense? Similarly, the total displacement at this point is 0. Sorry, the displacement at these 2 points are 0. Now if you come here and if you compute the displacement at this point also the displacement will be 0. So it is something that you have to keep in mind, because when you have a dissimilar cross section, then the middle portion moves, but if you have the same cross section throughout, then it is stays at the state of 0 displacement. Thanks for watching.